Now we are working on section 2.2, limit of a function and limit loss. So two concepts we will work on. The first one is to introduce limit of function. We're going to see in the future we use this notation, limit LIM of the function, but this limit is always go with x. So you want to see what's the value x goes. That's the notation. And the second concept we will work on will be limit loss. We will see some properties of limits. Okay, now let's see example 1. How does the function f(x) equal to x squared minus 1 divided by x minus 1 behave near x equal to 1? So near x equal to 1. First, let's look at what will happen if x equal to 1. We can see here, when x equal to 1, denominator of f(x) is x minus 1, which is 1 minus 1 equal to 0. Okay, then we know a fraction should not have denominator equal 0. In this case, f(x) is undefined at x equal to 1. And in the graph, we can see there will be a hole in the graph. At x equal to 1, we have to take this point away. So there's a hole over here. However, if we look at how the x value goes to 1, so for example, we can go from the left side to 1, and x can go also from the right side to 1. So it showed on the graph that will be this way. Go from the right side, come to this direction, and also go from the right side from this direction. Okay, you see here, as x goes to 1 from the right. Oh, sorry, let's try from the left first. From the left, the function in fact come very close to this point. This point is 1, 2. Okay, so function in fact goes to the point 1, 2. That means our f(x) in fact goes to 2. Okay. If we look at x goes to 1 from the right side, okay, showed in green, we can see over there the function in fact also come close to the point 1, 2. And we find our f(x) is also goes to 2. And since both sides go to the same target, now we can say the limit of f(x) as x goes to 1. So as x goes to 1 means go from both sides, from left and right. This limits equal 2. So now you see these two numbers. From left side, from right side come to the same target. And we can write the limit notation as limit of function fx as x goes to 1 is limit equal to 2. So we introduce this new notation. Okay. Now let's try some competition. Now we still look at this function. We want to choose different values of x as x goes close to 1 from both sides of 1. See what's the value we have. Well, x equal to 1.5, in fact, we get 2.5. Yeah, you can plug in your calculator. Let's finish this chart. We can see from this chart, when we choose the value 1.5, 1.1, 1.01 to 1.001, which is all greater than 1. So this group, in fact, is x goes to 1 from the right side. And we find the y value of x, in fact, is goes to 2. You see, these values are very close to 2. Now we look at the value 0.5 to 0.9999, and then those values we choose is come to 1 from the left side. We find the value of the function fx is also close to 2. Fx close to 2. This is how we think about limit. Let's see the definition of a limit. Suppose fx is defined on an open interval about c. So this interval this is an interval around c. However, it's not necessary to be defined at c. If fx is arbitrarily close to the number L, okay, you can see here, close to the number L, as close as we like, for all x sufficiently close to C. So if x close to C and fx close to L, then we can say f approaches the limit L as x approaches C. We can write limit of fx as x goes to C equal to L. So for the previous example, we can say fx approaches the limit 2 as x approaches 1, and we can write it as limit of fx as x goes to 1 equal to 2. So including two parts, you should have fx, you should also have the trend for x over here is x minus 1. So we can see here, there's another example. We can see the limit value of a function does not depend on how the function is defined at the point being approached, which is we don't worry about, for example, we have x approach to c, so it doesn't matter how it's defined at x equal to c. For example, we have a, the function is x squared minus 1 divided by x minus 1. When we choose x approach to 1, you want x approach to 1, is approach to this whole. However, it doesn't matter. And for the second one, we define gx is x squared minus 1 divided by x minus 1, when x not equal to 1, which is the same graph as A. However, this is a piecewise defined function. We defined x equal to 1 and gx equal to 1. That's why you have another point. So you have a hole and another point. However, when you consider limit when x goes to 1, you still look at from both directions. Approach to 1 from the left side or approach to 1 from the right side. Okay, they still come to the point 1, 2. Or we can define the function fx, hx equal to x plus 1. When x goes to 1, then you can approach the function from two ends. They still come to this point, 1, 2. We can see here all of the three functions has the limit equal to 2 when x goes to 1. So for the first one, we have limit of x squared. Let's just use notation fx when x goes to 1, limit is 2. The second one, limit of gx when x goes to 1, the answer is 2. For C, limit of hx when x goes to 1, the limit is 2. So really, the limit of a function does not depend how the function is defined at the approaching point. Let's see example 3. See some functions. The first function, if we have fx is x, and this function is the identity function, means x value and the y value is always the same. We want to find the limit for fx when x goes to c. You can see over here, given any point, you have c, c. And when the function approach to c from the left side and from the right side, they both come to the point cc, which we have limit of fx equal to c. Second one, we look at a constant function. If f is a constant function, fx equal to k, now k is any constant. For any value of c, the limit of fx, you can see over here, you choose x equal to c, now you have this point, the value will be ck, so y value is always k. Then the limit of fx, that should be k. We can use some other examples, similar examples, but with numbers that may be a little bit easy to see. So for example, we have identity function fx equal to x. I want to find the limit of fx when x goes to 3. Okay, let's draw the graph. Identity function, the graph should be straight line with 45 degree over here. Okay, I want to find x approach to 3. So approach to 3, you can see the point. Let me redraw this one. This is identity function. If I have x equal to 3, in fact, y is also 3. So you have this point. This point is 3, 3. We want to find the limit when x approach to 3. That means you go from the left side, you can go from the right side. Both sides approach to the point 3, 3, give you y value equal to 3. For the constant function, we can also use some numbers instead of use c and k. So if we have constant function fx equal to 5, so it doesn't matter what's the value of x, the y value is always 5. We can draw a graph. So always 5. And now I want to find the limit of fx when x approach to 2. So let's see. So here is 2. Then we can find the point on the graph is over here. This point is 2, 5. When x approach 2 from left side, no, go from the left side, approach from the right side, they both come to the same point, 2 and 5. And the limit of fx when x approach to 2 equal to 5. If we have graphs, in fact, it's pretty easy to see the limits. And a lot of times, a function may not have a limit at given point, okay? May not have limit at a particular point. So for example, the first, let's see, a unit step function. For this step function, we want to find the limit when x goes to 1. Okay, x goes to 0. We can see over here, when we approach x equals 0 from the left side, it comes to this point. However, when x approach to 0 from the right side, the function in fact approach to 1. You can see here, they do not go to the same targets. So this one do not have limit. This is no limit. We see second function. This is the reciprocal function. fx equal to 1 over x when x not equal 0, and define x equal to 0, then y equal to 0. Okay, now let's see this function. Suppose we want to find the limit when x goes to 0. Okay, we still look at this one. And the first one is no limit. Or we say limit doesn't exist. Does not exist. We say D and E. Now let's look at B. When x goes to 0 from the left side. Okay, we go from the left side, go this way. In fact, this function go down. Okay. Then we look at the function approach x to 0 from the right side. Okay, from right side, it goes this direction, and the graph, in fact, is going up. You can see over here, they do not approach to the same point either. So we say limit does not exist. Okay, does not exist. Part C, the function is very strange. It's changed a lot. You can see here, from left side approach to 0, and from the right side approach to 0. Even the values are very close, however, would not goes to 0, and this is also do not have a limit. Okay, this is some special examples. This is when we have graphs, we can find the limit pretty easy. We can tell the limit exists or not exist. However, a lot of times we really don't know the graph, and then the limit laws will be very helpful. Okay, This is the law for the limits. We can add two limits. We can find the difference of limits. We can multiply by constant. We can multiply two functions, find the limit. We can also divide two functions, and you can find the limit. The power rule, root rule still apply. Okay, so you may want to put this in your formula sheet. That may be useful for the exam. And we also have two other very useful series. The theorem 2, limits of polynomials. So if you have a polynomial function and the limit of this polynomial function for x goes to c, that will be the value of the polynomial function at x equal to c. Basically, what you do for polynomial function is plug in whatever the c value is. Theorem 3, if you want to find the limit of rational functions, you can also use it. The limit of the polynomial function, in fact, when x goes to c, rational function when x goes to c equal to pc divided by qc. So over here, we emphasize qc should not be 0. And if qc equal to 0, then we have a different way to solve it. That will be a different story. Now over here, we're going to just discuss the case when the denominator is not 0. Now we're going to see some examples. Let's see the first example. Limit of function x cubed plus 4x squared minus 3 when x goes to 2. We can see here function x cubed plus 4x squared minus 3 is a polynomial function. What's going on? Crazy. So x cubed plus 4x squared minus 3. This is a polynomial function. Okay. So we can use theorem 2. Which means the limit of the polynomial function when x goes to c, what you do is just plug in x equal to c to the polynomial function. That will be your limit. So for this one, we plug in x equal to 2 to the polynomial function. That will be 2 to the third power plus 4 times 2 squared minus 3. So that's 8 plus 16 minus 3. 24 minus 3 is 21. So we have the first one, limit is 21. Part B, the limit of x to the fourth power minus x squared minus 1 divided by x squared plus 5. Over here we can see you want to find the limit of the quotient of two polynomial functions. So we have px divided by qx, both px and qx polynomial functions. Okay, you want to find this limit, you should use theorem 3. Okay, theorem 3. What does theorem 3 say? It says limit of the quotient of two polynomial functions when x goes to c, that in fact you only need to plug in x equal to c to this quotient. Okay, to this quotient. However, be very careful. QC should not be 0. If QC equal to 0, then you cannot do this way. Have to emphasize this. Let's look at our question. X approach to -1. So first, we want to see if our denominator equal to 0. When x equal to -1, the denominator x squared plus 5 is -1 squared plus 5, which is 6. That's not 0. Okay, that's good. We can use theorem 3. So limit x goes to -1 of this rational function. Denominator will not be 1, so we just plug in x equal to -1. -1 to the fourth power minus -1 squared minus 1 divided by -1 squared plus 5. Okay, the top, that's 1 minus 1 minus 1 divided by 6. The answer is -1/6. Let's see C. We want to find the limit of the square root given x approach to 2. So we can use our square root rule. It's the limit when x goes to 2. That should be limit of this function, and then take square root. You take it out. Inside, the function is a polynomial function, so we can just plug in x equal to 2. That'll be 4, 2 squared minus 3. 2 squared times 4, that would be 16 minus 3. So you have square root of 13. That's very nice rules you can use. I would like you guys really practice those rules. Make sure you remember those rules and practice the homework questions. You will feel so good. It's nothing too difficult, really. Over here, we needed to remember that 0 divided by a non-zero number is 0. So we can see here 0 divided by a non-zero number equal to 0. This is when a not equal 0. Okay. However, if you have a divided by 0, this will be undefined. No, denominator cannot be 0. Sometimes if you look for limit, you may see something look like 0 divided by 0. This is also not defined, but we make it indeterminate. Okay, in limit questions, you may have different answers in different cases. And a lot of times, if you get 0 divided by 0, these tell you that the original functions can be factored and reduced. Once you factored and reduced the function, then you can calculate the limit. Now let's see this example. We plug in x equal to 1. Okay, we don't calculate the limit yet because we don't know what's the... No, we already did this question, right? When x goes to -1, we check the denominator first. Okay, when x equal to -1, then the denominator x squared plus 5 is -1 squared plus 5 equal to 6, which is not equal 0. That's a good thing. We can calculate the limit directly in this case. Denominator is not 0, and this is a rational function. We can just plug in the value of c. Over here, the value of c is -1. So plug in. So -1 minus 4 minus 3 divided by 6. The top is -8. Then we have -8 over 4. Reduce the fraction, -4 over 3. Let's see example 6. This is also a rational function. So first step, we needed to check the denominator. When x equal to 1, the denominator x squared minus x, that is 1 squared minus 1, equal to 0. Okay, the denominator is 0. That may have problem. So that means the rational function is undefined at x equal to 1. In this case, we should check the numerator as well. So numerator x squared plus x minus 2, that is 1 squared plus 1 minus 2, also equals 0. Okay, now pay attention here. Both numerator and denominator equal 0. So we will see it look like 0 divided by 0. In this case, this indicates, so this means the original function can be factored and reduced. In this case, we should factor both top and the denominator and simplify the function before we find the limits. I know a lot of people really don't like factoring polynomials. However, this is something you needed to know how to do. Now we can see limit of x goes to 1 for function square x squared plus x minus 2, denominator x minus x. So we keep writing x squared plus x minus 2. We can find two numbers, multiply to make a -2, add to make a 1. So we have x plus 2 times x minus 1. Denominator x squared minus x, factor out the common factor x, then you have x minus 1. We can cancel out x minus 1, x minus 1. Reduce this function as x plus 2 divided by x. X goes to 1. We can see here, in this case, the denominator is not 0 when x goes to 1. We can plug in x equal to 1, and 1 plus 2 divided by 1, which is 3. Let's see another example. Example 7. If the function is given as a graph, how can we find the function, find the limit of the function? Okay, let's see the first one, f -1. I hope you didn't forget this this notation. F -1, that means the value of the function at x equal to -1. We find the point. So this is the point for a. So f -1 equal to 0. Next, we want to find f1. That means when x equal to 1, what's the value of y? From the graph, we can see x equal to 1. There's a hole over here. That means when x equal to 1, the function, in fact, is not defined for the under piece. However, it's defined on the other piece over here. So it's defined over here. So we see f1, in fact, equal to 1. Now let's see C. What is the limit of function f(x) when x goes to -1? You want to see x goes to -1? We can approach -1 from the left side and the right side, okay, from the both sides. We can see over here, when x approach to -1 from the left, the value of y, so f(x), in fact, goes to the value of -1, which is 0. If we have x goes to -1 from the right side, okay, from the right side, we can see the function, in fact, go from this direction, okay, go from this direction, which is goes to f -1. That's also 1. In this case, we can see the function, in fact, has a limit of 0 when x go to -1. Let's see part D. What is the limit when f(x)? What is the limit of f(x) when x goes to 1? And now we can look at this point at 1 over here. We can see here when x goes to 1 from the left side. So we look at the bottom piece is over here. And the f(x) in fact goes to the hole. At the hole, y value equal to 0. When x approach to 1 from the right side, so go this way, from the right side, and the function, in fact, is on the piece from 1 to 2. On the right side, the value of the function f(x) is turns to 0.1. We can see here from two different sides, left and right, the target of f(x) is not the same. One side goes to 0, the other one goes to 1. In this case, we say this limit do not exist. So we sometimes just write D and E, okay, do not exist. This shows you how we approach different directions. Keep in mind, if the limit exists, you should have the same target from the left side and the right side approach to the same point. Next, we're going to see the sandwich theorem. This is a very useful theorem. This theorem says if function f(x) is between gx and hx, so fx is our target, and gx, hx are the bound. Then we say if the two bounds has the same limit, then the function f(x) also has the same limit. Then just like a sandwich, push it to the same target. Let's see some examples. Example 8. Sorry, it seems didn't show up. Okay, so this is the example 8, which is not showed over here. And we have a function ux is between two functions, 1 minus x squared divided by 4, and the function 1 plus x squared divided by 2. So it's bounded for these two functions for any x not equal to 0. That means we don't look at x equals 0. There's a hole at 0. Okay. Now the question is, find the limit of ux when x goes to 0. So over here we say no matter how complicated u is. So over here, we really don't know what ux look like. I just know ux is bounded by the two functions 1 minus x squared divided by 4 and 1 plus x squared divided by 2. So we can think about sandwich rule. However, first we need to see if the two bounds given the same limit. So let's see here. The limit, this is one bound, lower bound, and this is the upper bound. Let's calculate the limit for the lower bound when x goes to 0. We can see here, this is a polynomial function. We just plug in x equal to 0. That will be 1 minus 0 squared divided by 4. So it's 1. Then we calculate the bound for the right side, which is 1 plus x squared divided by 2. This is also a polynomial function. We can plug in x equal to 0. So 1 plus 0 squared divided by 2 also equal to 1. Now we can see here, this function is bounded by two functions. The both bounds has a limit equal to 1. Now we can use the sandwich theorem. We say the limit for the one bounded in the middle when x goes to 0 should also have the same limit equal to 1. The sandwich rule is very useful. Using the sandwich rule, we can establish some very complicated functions, the limit of complicated functions. So for example, we have sine theta. We know sine theta is between, the value is between -1 to 1. However, when theta equal to 0, what the limit should be? If we look at the graph, in fact, we can see the limit of sine theta when theta goes to 0 should be 0. So basically just come to this point. That's not too complicated. However, we can consider sine theta is bounded by y equal to absolute value of theta and negative absolute of theta. Then we can find the limit. The same way, we can find the limit of cosine theta when theta goes to 0. And this, in fact, that's equal to 1. This graph is not correct. Okay. The graph in fact showed us is 1 minus cosine theta. In fact, cosine theta graph should look like this. So over here, this is pi over 2. So this is 0. This is pi. And then this is negative pi over 2. We can see here, when theta goes to 0, it comes to this point direction. So in fact, this cosine theta goes to 0. That is the same as the limit of cosine 0, which is 1. Okay, so the graph is showed y equal to 1 minus cosine theta. We have another theorem can help us to decide the bound of the limit. We say if function fx less equal than gx for all the x, keep in mind for all x in a given interval, and then if the both limits of f and g exist, then they should have the same direction of the limits. So the limit of fx should be smaller or equal to the limit of gx. This kind of theorem mostly will be used to improve something or when you need to check your answer. Okay, so this is everything for this section. Please make sure you practice and send your questions if you have any. Thank you.